Greetings, my name is John Gabriel, and today I'm going to talk with you about the theory of fractions. And I'm going to show you how you can derive all of that theory simply from one of Euclid's propositions, a very important proposition. It's found in Book 5, and it's proposition 12. So I'm going to show you the proposition and then show you how to derive all the theory of fractions, including the binary operations of multiplication, division, addition, and subtraction. So let's begin. So now, let's look at the proposition very quickly. The proposition says that if x over y is in proportion to p over q, then x over y is equal to p over q is equal to x plus x over y plus y. And as long as we add the antecedents to the consequence, whatever we obtain will always be in proportion. And so using only this one property, one can perform all arithmetic operations with using only the primitive notions of subtraction and addition. And of course, addition is based on subtraction. So let's just take a look at quickly what that means. I'm going to come to this example later. So I'll just put it up there as an exercise, which I'll do with you. Now, suppose you have 3/5, right? And you can take anything else that's in proportion. So if, for example, you multiply these two, well, let's just do this. Let's just add this thing to itself, right? And what do we get there? We get 6 over 10, right? So 3/5 is equal to 6 over 10. And we could also just add 6 over 10 here. Yes? And then what would we get? We'd get 12 over 20. All right? So, and the reverse process is true too. In fact, we really should have started with subtraction, because subtraction is the most primitive operator. So if we subtract from this, let's say 3/5 and then 6/10, whatever we have will still be in proportion to 12/20. So in this case here, it's 12 minus 9, which is 3, and 20 minus 15, which is 5. Okay, and this, of course, is the irreducible form as we know it. And all this can be done with pure geometry, as I'm about to show you now. So let's look at a demonstration. The way this works is with similar triangles. So you see, if two triangles, this large one is similar to another one, like that, then we can add these lengths, and we'll always have the same ratio. Okay, so I've put in the representation in base 10 here, and you'll see that it doesn't matter what I do, whether I move this up or down, it's always 1.17, okay? If I go out of there, naturally nothing. So I can add anything to the top part and anything to the bottom part as long as that particular fraction is in proportion. And also I can subtract it from the top and the bottom part. So as long as the fraction is in proportion to what is given, either of these, then subtracting or adding the antecedent and consequent will give me another fraction that's in proportion. In other words, it's equal. So the antecedent is always what appears on the top of the vinculum, and the consequent on the bottom of the vinculum. Also, you could call that the numerator and the denominator, okay? So now, we can also do this geometrically. So if we're subtracting or adding, so if we want to subtract something from this top part, let's say, let's just put on the grid here so we can see what's going on. Whoops. Grid. Okay, so the grid, so if we want to subtract a part, then we're going to get that, right? And so we can see that we can subtract any amount and we can add any amount. Oops, I'm somehow not able to drag that. I don't know why. Strange. All right. I was supposed to be able to drag that, but that's not a problem. That's not a big deal at all. In any case, we can subtract and multiply, and we can also divide and multiply using only geometry, right? So if we extend these like that, then what this says is that the length of this line here multiplied by this line will always give us this length, provided the length of this line here is 1, okay? So if this length here is 1, then let's do that quickly. Let's just put the grid on here so I can see what I'm doing. So if this is 1, that's good. And now, let's say we want to multiply 2 by 3, okay, and 3 by 3, and 3 by 3 is 9, and 2 by 3 is 6. So you can multiply and divide geometrically without using any numbers whatsoever. So now, and we also saw that you can have the same thing here with straight lines. In other words, subtraction and addition. Subtraction means you simply move that along like that, okay? Or add to it by doing that. So we can do all things in arithmetic just through pure geometry. So now let's look at arithmetic with fractions. And the first thing I'm going to show you is the quotient. Well, we could look at cancellation too. But before I get to cancellation, let me look at the quotient, because we already have a good idea what that is. So the quotient requires no prior knowledge. It uses only what is given. So supposing we want to divide 2/3 and 1/5. Well, we're really just forming this quotient, aren't we? We're saying 2/3, 1/5. Or if we write it using the vinculum form, it's 2/3, 1/5. Okay, so we get rid of that. Very good. Now, we'll come back to this in a second. So now over here, what we do is we just simply take this and add it to itself 5 times. 1, 2, 3, 4, 5. Or take the sum, which is 2/3 plus 2/3 plus 2/3 plus 2/3 plus 2/3, which will give us 10/3. And likewise, we do the same to this side if we want to make it a 1, or we could just add this to itself 3 times, and then we'd get the same denominator. So on this side here, you get 10/15, right? Okay, you get 10/15. So depending on how you want to do this, let me give you an example here. Let's go to this here. And so I could start off with this side here, and let's say, let me add it to itself 3 times, like so. 3 times. Because it's in proportion, yes? Divided by 2/3, and let me add 2/3 to itself 5 times. Plus 2/3 plus 2/3 plus 2/3. Yeah, so we'll have on this side here 12/15 divided by 10/15. And since these consequences are the same, we're really looking at the ratio 12/10, and we're done, right? So what we've really said here, this is A/B divided by C/D. Oops, didn't want to do that. C/D. Then what we're going to have is AD/BD divided by divided by CB over BD, right? Which is the same as AD divided by CB, yes? And of course, this leads to the same thing when we say 4/5 divided by 2/3 is equal to 4/5 times 3/2, all we're doing is we're saying A over B divided by C over D is equal to A over B times D over C, right? And so that again will give us AD over BC, right? So now you can see why you flip the second fraction so that the consequent and antecedent switch places. And so 12/10 is the answer. Now, provided you know something, if this is not in its irreducible form, then provided you know another fraction that is in its irreducible form, you can subtract it from this. So for example, I know that 6/5 is in proportion to this. So I can say 12/10 minus 6/5 will give me 6/5. And that is equal to 12/10, which is equal to 1.2, okay? So coming back to this, all I've done here, now in this particular case here, I've added all these up and said 10/3. And on this side here, I said 1/5 plus, because I've added I've added these as fractions. I haven't actually added them as being in proportion to each other. So it is 10/3 because we've got 1, 2, 3, 4, 5, and 5 times 2 is 10, right? Alternatively, in this particular case here, we could have said 10 over 15, right? And 5 over 25. So there are many ways of doing this. But what I chose to do here is to, because this was 1 over 5, to reduce it to 1, which I could do by simply saying, just add it to itself another 4 times, 1, 2, 3, 4, 5, and I'll get 1, right? Because 5 times 1/5 is 1, correct? And then that just makes this a lot easier, because if I'm dividing anything by 1, it's just itself, which is 10/3. So that's the quotient. Now the product is just the reciprocal of the quotient. So I can take any one of these 2/3 and divide it by the reciprocal, and all I do is the same process. I just continue to expand it out like this, in which case I'll get 5 on the top here and 1 on the bottom, and then I could work with the left-hand side and add it to itself 2 times, so that I'll get 6/3 over 15. And finally, I could say it's 6/3 minus 2 over 1 twice over 15, yes? And that will give me 2 over 15. I could also do this example by using the reciprocal of 2/3. So if I say, let's do that one. That's 1/5. I didn't mean to do that. 1/5 divided by 2/3. Okay, so I'm starting a lot of things up here, which I don't mean to. So now let's go back here. 1/5 divided by 2/3. Let's just clear this. New, I don't want to save that. So just to be sure, it's 1/5 multiplied by 2/3. Okay, so we'll have 1/5 multiplied by 2/3, which is really the same as 1/5 divided by 3/2, okay? And then we just repeat the process. We can say that's the same as 1/5 plus 1/5 divided by 3/2 plus 3/2 plus 3/2 5 times, right? Which will give us 2/10. 1, 2, 3, 4, 5. That's going to be 15 over 1, 2, which is 10, right? So because these are the same, that's equal to 2/15. And that is, of course, the answer. It's 2/15. So you've seen how to do this using only the similar triangles, right? As you saw from this particular demonstration. All you do is you use similar triangles, and you can do all of the operations, right? So we've covered the quotient and the product, and addition and subtraction are done the same way, which we've been simply using all along as per the cancellation. So it can be, as long as this, if we choose any one of these, as long as we find a fraction that's in proportion, which is, by the way, determined by cancellation, this fact here, we can multiply the antecedent and the consequent by the same length, and then this will always be in proportion, right? We can also divide it, because multiplication is just a reciprocal of division. So as long as we find something in proportion, as long as 2 over 1 is in proportion to 10 over 5, we can just keep on subtracting it until we get 2 over 1. And so that will be the final answer, or the irreducible form that we need. And in summarizing, what does this fraction tell you? Well, the Q tells you how many equal parts of the unit are being considered. How many equal parts of the unit are there? There are Q equal parts. And that's why Q is called the denominator, and P is called the numerator, because the P tells us how many of these equal parts are being enumerated. And so the rational numbers are the only true numbers. There is no such thing as an irrational number, okay? 22 over 7 is not equal to pi. It's not even an approximation for pi. In fact, the values that we use for pi are truncated and are not really equal to pi. So that's really all the theory of fractions you need to know, and everything you need to know about numbers, all in one proposition. This beautiful proposition of Euclid, Book 5 and Proposition 12, tells us everything. I could have replaced all these plus operators here by the most primitive, which is the negative or the difference operator. I can subtract them, okay? All right, well, very well. You might have noticed something here. If I had, for example, let's just go new like this, new, get a new one, okay. If I had 3 over 4 and I decided to subtract that, I would get 0 over 0, right? And now the Greeks didn't have 0 as a number, didn't consider 0 to be a number. So, you know, I mean, while you can say 3/4 plus 3/4 is equal to 6/8, it's strictly speaking not correct to say, to do this. Although in terms of the right angles that you saw early on, if we had to move these right down, shift these right down so that we have no lengths on either side, we'd have 0 over 0, wouldn't we? But if this happens, then we know that the fraction that we have has reached an irreducible form. Of course, if we start off with 6 over 8 and we say minus 6 over 8, well, that doesn't tell us it's irreducible. But we're assuming that we have a fraction, in this case, which is in proportion to this fraction here and in irreducible form. Okay, so if we subtract the irreducible form from any other fraction, we will eventually get to the irreducible form. So, and if we don't stop, we'll get to 0, 0. So if we start off with 6/8 or 9/12 and we subtract 3/4 continuously, let's say 3/4 there and another 3/4 there and another 4. So 9 minus 3 is going to leave us with 3. And 12 minus 4 is going to leave us with 4, which is the irreducible form of the fraction. So 0 isn't a number because it doesn't measure anything, okay? 4 is a number, 3 is a number, but 0 is not strictly speaking a number, even though it is very useful. And the greatest use of 0 is in communicating and removing ambiguities when we talk about numbers. Also in equations, where acts as a placeholder. Well, I hope you've enjoyed that and that you'll join me again next time for another interesting video on some other topic. Till next time, my name is John Gabriel, and this is New Calculus Channel. Goodbye.